Okay, we'd better start. Today is going to be a relatively easy day, you'll be pleased to know, and we may even finish a bit early. Tomorrow is going to be fairly full, so maybe what we could do at the end of today is if you have any questions throughout the whole of the course that you'd like to raise, then maybe the end of today would be the time to do it. So perhaps you might be thinking about whether you have any issues that you'd like to raise. If you don't, then that's fine, and you'll be able to go off earlier. Okay, so we're going to talk about two topics today. One of them is chemical mechanisms. And then what we'll do is we'll talk about NOx chemistry. NOx chemistry is important because combustion is one of the major sources of the emissions of nitrogen oxides into the atmosphere. And as we'll see tomorrow, that has a variety of issues, a variety of results. And so what we like to be able to do with combustion systems is to minimize the amount of NOx that's emitted. And so what we'll do is it's a very selective set of topics, but it's related both to the production of NOx and ways of reducing the amount of NOx in combustion systems. So that's going to be the second part, but initially what we'll do is we'll talk about chemical mechanisms. Now, we spent a lot of time talking about individual chemical reactions, elementary reactions, the way in which we measure them, the way in which we calculate them theoretically, the way in which we put the two methods together. As combustion people, though, the ultimate aim of these measurements and these calculations is to be able to put the information, the kinetic information, into chemical mechanisms. And then for those chemical mechanisms to be used in combustion systems. What I'm talking about are detailed chemical mechanisms. So these are mechanisms with many chemical reactions in them. Many of you are fluid dynamicists. Many of you do fluid dynamic calculations of combustion systems with chemistry in them. And one of the important issues there is that you can't put all of this detailed chemistry into your CFD codes. And so one has to go through a process of lumping or reduction. And that's not really one of the issues that I'm going to talk about. I'm not competent to talk about it. And so I'm going to restrict our discussion entirely to these detailed chemical mechanisms and accept that somebody somewhere is going to have to do a good job on reducing them in magnitude so that they can go into your CFD codes. But there are two things that these detailed chemical mechanisms do. One of them is they provide the basis that can be used for this lumping or reduction process. And secondly, they provide a means of evaluating reduced mechanisms. So you can test a reduced or lumped mechanism against a detailed chemical mechanism. And the detailed chemical mechanism should have a better chance of being correct than the lumped one. And so it provides a good test of those reduced chemical mechanisms. Okay, so we're going to look at ways in which mechanisms are constructed, their dependence on rate and thermodynamic data, and their evaluation using experimental targets. So they're complicated entities. There are many uncertainties in the parameters that go into them, and so we need to be able to test them against experiment. Okay, a hierarchical approach is generally used in constructing chemical mechanisms. And so what you do is you start with the simplest chemical mechanism and you build up from there. And you can find a discussion of this approach way back in 1981 by Westbrook and Dreyer of this approach to hierarchical mechanisms. It's a logical approach to use, but it's also scientifically sensible as well, because this base mechanism, the hydrogen-oxygen mechanism, plays a key role in just about all of the chemical mechanisms that we're dealing with. So these are examples of hydrogen-oxygen mechanisms. So Lee et al. From 2004, Konoff 2008, Hong 2011. And these are examples of the hydrogen-oxygen mechanism. And one of the key papers that you need to read in this, if you're interested in this hydrogen-oxygen system, is this paper that I mentioned a couple of days ago by Burke et al., which reviews many of the chemical reactions that are involved in this mechanism. So here are some examples of using these mechanisms to compare them with results, experimental results. So these are laminar flame mass burning rates at different pressures, 5 atmospheres, 3 atmospheres, 1 atmosphere. And these are the results of simulations using mechanisms. The solid line is the Lee et al. Mechanism, and the dashed lines is an earlier mechanism on which it was based, derived from by Muller. And you can see that the agreement is really very good and a significant improvement on the earlier mechanism. So one can say that as far as mass burning rates are concerned, this Lee mechanism is doing really quite well. And then these are ignition delays in hydrogen-oxygen argon mixtures in experiments carried out in shock tubes. And again, the full lines are the Lee mechanism, and the points are experiments. And you can see, once again, reasonably good agreement with these ignition delays using these mechanisms. So this is this latest mechanism from Hong et al. And I've shown this slide about 3 times now, but it demonstrates very clearly how well this H plus O2 going to OH plus O reaction is defined using high temperature shock tube data from Maston et al. And from Hong et al., covering the temperature range from about 1,000 K to about 3,000 K. So this branching step here is really very, very well sorted out. Then this is a reaction in which there's much more uncertainty, OH plus hydrogen peroxide. Here's the experimental results from Hong et al. Here's the Hong et al. Fit to those data. So that's the rate coefficient for OH plus hydrogen peroxide. And this slide compares those results with estimates with parameterizations of the rate coefficients for this reaction in a range of mechanisms. This is a mechanism from Galway, and this is GRI mech, which we'll talk about in a minute. So you can see that different mechanisms have got different rate coefficients in them. And if you find, and we'll qualify this later on, but I think we're talking about this at breakfast. We never stop talking about combustion, you see. It's, we're talking about this at breakfast. If you have a chemical mechanism that's a fundamentally based chemical mechanism, as these are, then if you get improvements in the rate data, then you need to put those improved rate data in the chemical mechanism. So these chemical mechanisms are going to evolve, they're going to change. And you need to keep testing them against experimental data, say those ignition delays, etc., to see how well things are going. But simply because they might not agree with those experimental data, that isn't the reason to not to put these improved chemical kinetic data into the mechanism. If there isn't an agreement, then what it's telling you is there is something else wrong. Sorry, yeah.
So I noticed right away that like GRI is like way off on this, and many of us like use that as like our a default or starting mechanism. Is there something that's like kind of like an open source, like we're basically, all right, we see these problems, but we don't want to like pull mechanisms from all these different papers. Is there some like repository where people have like an updated GRI or something like that?
No, I mean, I'll talk about GRI in a few minutes. And GRI has specific issues associated with it. It's very, very widely used. But there are health warnings associated with it that you have to accept. Michael Franklak in Berkeley has tried to develop this sort of repository. I mean, really, this is if you like, this should be a community project where there should be community mechanisms developed together. But that isn't the way the field works, at least at present. There are different people developing mechanisms, and they have different aspects which are good and bad. But we don't yet live in a nirvana where there is a beautiful repository of the best chemical mechanisms available. It's the same it's not just combustion. I'm heavily involved in chemical mechanisms in atmospheric chemistry, and it's the same there. There is a lack of agreement, and part of the problem is that all of these chemical mechanisms, this is an important thing to remember, especially when you go to more complex systems, they are underdetermined. So the parameters have to be estimated. They're not, we haven't been able to measure all of the rate data that we need. So the mechanisms are underdetermined, and necessarily they have good and bad points. The thing about GRI mech, as we'll discuss in a minute, is that it's tuned, and that brings issues with it. Okay, this is this Burke et al. Paper. I gave you a reference to it earlier on. And these are examples of these reactions, H plus HO2. And H plus HO2 is a very, very important reaction because it's leading to a competition between the reaction of HO2 with itself and reaction of HO2 with H here. And the interesting thing about it is that there are two channels. There are two important channels in the reaction. H reacting with HO2 and forming two hydroxyl radicals, and H reacting with HO2 and forming H2 plus O2. And in this case, you can see that you're replacing a highly reactive radical and a relatively slowly reacting radical with two fast-reacting radicals, OH. And in this case, you're replacing them with stable molecules, H2 and O2. And so the competition between these two channels is absolutely key. And so these are, this is an analysis from this Burke paper of these two channels, the overall rate coefficients and the branching ratios. So this is the rate coefficient for a particular channel versus the overall rate coefficient for H plus HO2. And you can, so this is the molecular channel, which these are the present calculations. So these are the Burke et al. Calculations. And this is the radical channel, and this is the molecular channel. And to a kineticist, or to a theoretical kineticist, which I hasten to add that I'm not, this brings very interesting theoretical issues to bear, because what is included down here are two ways of approaching. So these two different results here, quite, well, not huge differences between them, but some differences between them, incorporate a particular way in which this reaction will occur, something called roaming, which I won't go into. But if you are interested in understanding in detail how chemical reactions, elementary chemical reactions occur, then I would strongly encourage you to read this paper by Burke et al. And especially the theoretical aspects of the way in which it's put together, in addition to these comparisons that they use between different parameterizations of these rate coefficients and channel yields from different sources. Sorry?
In that paper, you're talking about present estimation or evaluation on the branch ratio. Does it mean the paper, the most recent paper by Berg et al. Or by yourself?
No, this is the paper by, no, not by me. This is the Berg et al. Paper. Okay. So what I'm saying, the Berg et al. Paper was published in 2012.
Yeah.
And it's the latest view, taking in work which was done directly for that paper as part of CEFRC and also available experimental data. So
for that particular topic, someone has possibly Europe has done a kind of version of continuous calculation on this particular system. We have determined the branch ratio, but I'm not sure how good it is. I think Berg may.
So who has done those calculations?
Europe has published in Japanese.
Okay, right, okay. Yeah.
I don't know how good it is.
No, but these estimates here, these dotted ones, these light ones, come from an analysis by the Argonne National Lab, by Stephen Klippenstein's group, on a very detailed theory for this reaction H plus HO2. Okay, so this is just a random reference for you for more complex chemical mechanisms. So these are rapid compression machine and shock tube results and the detailed chemical mechanism. And the mechanism comes from the group of Henry Curran in Galway, and it's dealing with these larger fuel systems. And obviously, as you go to these larger fuel systems, there begins to become more and more disagreement between these different mechanisms. But one of the contributions that's come from CEFRC is an attempt to understand mechanisms of this sort of magnitude, C1 to C4, C1 to C5, in more detail, especially as you begin to put oxygenated systems in. And we'll talk about that a little bit more later on. So here's another mechanism that comes from Henry Curran on dimethyl ether. And I put this up because this is one of the things that we were talking about yesterday, the oxidation of dimethyl ether as investigated using pulse photolysis. And so just let's step through it and see what's going on. So we've got this radical here formed by abstraction from dimethyl ether, and that can dissociate. So one of the things that it can do is it can dissociate. These are the reaction numbers, so you can see this is a relatively large mechanism. This can dissociate and form CH3, or it can react with O2, forming this peroxy radical. The peroxy radical can isomerize to form this hydroperoxy radical. So what's happening here is a hydrogen atom is being transferred, as we discussed yesterday, from the CH3 group to the O2 group, forming a carbon-centered radical and this hydroperoxide group. At the time, this had not been measured directly, and so this illustrates the way in which mechanisms are constructed. Rate parameters are estimated, and they're not plucked from the air. They're estimated on the basis of reasonable chemistry and an understanding of the way in which reactions occur. And so this is saying that the activation energy for this reaction depends upon various contributions. One of them is the enthalpy of reaction. The other is the energy of abstraction, and the other is what's called ring strain. So what is happening here is that we've got what's happening is we're transferring this hydrogen atom here from this carbon atom to this oxygen atom here. And the ease with which that occurs depends upon the size of this ring here. And for a 6-membered ring like this one is, it's a reasonably optimized process. As you make the ring smaller especially, but also if you make it bigger, then the ring strain, that there is an energetic requirement, and that's described through this ring strain term here. And then this is finally the abstraction energy, which is based on a wide range of measurements for a whole range of systems of the ease with which this hydrogen atom is abstracted from this carbon atom by this peroxy group. And I've dwelt on this because this is an approach which is so very central to the construction of mechanisms, because we don't have all of these measurements available to us. And obviously, the uncertainty in this parameterization is going to be significant. And the more we can measure processes of this sort, and this has now been measured, then the better placed we are. And so then this hydroperoxy radical here can dissociate to form OH. So this, as we said yesterday, is the propagation step. It can react with O2 to form this species here, which in turn can form a stable molecule and OH. And this stable molecule can fall apart and form 2 radicals. And so this is the branching step, and this is what we called yesterday the degenerate branching agent. And so that's the sort of mechanism that Henry Curran has within this dimethyl ether approach, this dimethyl ether mechanism. And notice that there is no inclusion of any of these things we were talking about yesterday, like well-skipping reactions and so on. And so the idea of well-skipping is almost certainly going to change the way in which we think about systems of this sort. And I also showed you a potential energy surface from Emily Carter's group. And that potential energy surface has a picture which is quite different from this picture that we have here, and allows for the fact that certainly at lower pressures, some of these reactions can occur from energized species before they've been fully collisionally relaxed. Whereas this traditional sort of mechanism presents a picture in which all of these species here are fully collisionally relaxed. They've got Boltzmannized distributions of molecules throughout energy levels. And that gives rise to, in the end, quite a different picture. This mechanism gives a pretty good description of what's going on in macroscopic systems, looking at ignition delays, looking at NTC behavior, so negative temperature coefficient behavior. And that's partly because there's been a certain amount of tuning of some of these rate parameters. And so in terms of being a mechanism which gives a reasonably good description of a range of processes, it's not quite so fundamentally based. It's not nearly so fundamentally based as the hydrogen-oxygen reaction system we were talking about. And so in a sense, this is a further comment on, is there a nice repository of accurate mechanisms available to us? And this is an example of a mechanism which perhaps isn't as accurate, isn't as correct at a fundamental level as it ought to be, but nevertheless it's a very useful mechanism for looking at DME chemistry in combustion systems.
I saw in your notes that most of the rate coefficients had been estimated. So how do you go about quantifying the uncertainty? Do you have an estimate based on thermodynamic data?
It's very difficult to do. It is extremely difficult to do. And I think in the end, it's something that I think all you can do is play around with it. You're not going to be able to sit down and say, well, the uncertainty of that rate coefficient is of the order of a factor of 3. I think what you've got to do is to look at sensitivity analyses. And I'll say a little bit about that later on. We need to be able to focus on what are the key reactions. The difficulty is that sensitivity analysis is a local process. So sensitivity analysis gives you the local sensitivity at a particular time for a particular reaction independent of other reactions, except in terms of how you got to that particular point in time. And so there are issues associated with sensitivity analysis, but nevertheless, it's a very useful tool. But there are other tools that we ought to be using that would give us a different pitch on the problem. Not a very lucid answer, but...
The previous slide, I have more questions about that one. So how, if you cannot measure the real constant, I guess, so how can you know these reactions are real? I mean, did you measure the intermediates, let's see, the chemical species, radicals, or molecules in the experiment? Or this just from theoretical prediction?
Yeah. No, they're not theoretical predictions. They're estimates. They're based on decades of chemical experience.
So they indeed define all these species, these chemical species, radicals in the experiment, right?
Sorry?
So all these chemical species and radicals, molecules are all measured in the experiment.
No, no.
So how do you
Well, that's what I'm saying. If you take a large molecule, then on the basis of our understanding of the chemistry of smaller species, we can understand the way in which it's likely to fall apart and the sorts of radicals that it's going to produce. And there are experiments which can demonstrate under particular conditions the way in which that would occur. And so we have this range of experience which allows us to construct these chemical mechanisms. So to think that, going back, to think that all of these species here have been detected and are included in the mechanism because they've been detected is to misunderstand the way in which chemical mechanisms are constructed. They're constructed on the basis of our general understanding of the way in which this chemistry is going to occur. And it could be wrong. You know, there could be serious deficiencies with it. For example, this species here, this hydroperoxy radical, there has only been one observation of that species. At least, I think, certainly a year ago, there had only been one observation, and that was in a flow reactor in China, using synchrotron VUV photoionization spectrometry. So there are good theoretical reasons why such species exist. We have good theoretical estimates of their stability and so on, and we have mechanistic studies which again give information on their stability and their reactions. But for these complex mechanisms, there are many, many, many of these species that we've simply never seen, and we infer from our general understanding and from general behavior. Tomorrow, one of the things that I'll do is I'll talk about atmospheric chemistry, and I'll mention some observations that were made in the Amazon, in China, in Burma, in field measurements, which demonstrate very clearly that under specific sets of conditions, there is chemistry occurring which we had simply no idea was occurring in the atmosphere previously. And funnily enough, it's associated with this sort of chemistry that we've got. It's just like combustion chemistry. It's the involvement of these hydroperoxy radicals, which had never been thought about in atmospheric conditions before at all. And so our understanding changes and evolves. And so we can't say at any given instant that these complex chemical mechanisms are the final say in what we're seeing. It's an evolving process. It's a research process. I hope I'm not completely putting you off the idea of chemical mechanisms. Chemical mechanisms are good things, and we need them.
There are many chemical mechanisms for just a one thing, right? So people all say, okay, this mechanism works well, but it turns out that. But how can you explain why? I remember the maximum combustion. There are 4 different models. The big point explain experimental method. It really surprised me.
Yeah, and being one of the people who've produced a mechanism for methane oxidation, which is different from other people's mechanisms for methane oxidation, the problem, as I've said, is that they are generally speaking, these mechanisms are underdetermined. We don't know, we don't have experimental data, except in the case of hydrogen oxygen. We don't have experimental data on all of the rate coefficients, and even on some of the species that are involved. And so there are going to be differences between them. And what we tend to do is to tune these mechanisms slightly to get them to agree with experimental data. And there are problems associated with that, as we'll see in a minute. OK, so GRIMEC. And many of you here will have used GRIMEC. So it's a list of elementary chemical reactions and associated rate constant expressions. Sensitivity tests have been carried out against experimental data. And then the rate parameters have been tuned. And they've been tuned within their ranges of uncertainty. The process of automatic simultaneous parameter optimization to get the parameter set for each successive release of GRIMEC. And there are strict constraints kept on the rate parameters within the predetermined bounds based on evaluations of the uncertainties and applications of conventional reaction rate theory. So this is an approach which is essentially a practical one. And it reflects what we've been talking about before, that we want mechanisms that are going to work pretty well, but we accept that there are significant uncertainties in the parameters that are contained within that mechanism. And so the approach which is used in GRIMEC is to tune, but to tune generally. I mentioned this methane mechanism that we generated in Leeds, and what we did was to look at sensitive reactions and then to tune these 1 or 2 sensitive reactions very slightly. GRIMEC takes in many ways, a much more scientific approach in which they do some selection, but it's based on a much broader sensitivity analysis than we used. So it's optimized as a whole. And the key health warning is that substitutions and further selective tuning should not be used. Okay? It's been tuned. It shouldn't be tuned any further. All reactions are reversible, and they're based on the data that I talked about right at the end of the lecture yesterday, the Burkat database from Technion. And you use it in conjunction with Chemkin. GRIMEC 3 has 53 species, 325 reactions. Optimized for methane as a fuel. It includes C2 and propane chemistry. And it's optimized against chosen targets in ranges 100 to 2500 K, pressures of 10 torr to 10 atmospheres, and mixing ratios, stoichiometric mixing ratios 0.1 to 0.5. So this is a listing of some of the reactions from GRIMEC. And the reactions in bold are those whose rate coefficients served as active parameters in the model estimation. So they didn't tune everything. They tuned the ones which are in bold. And those in red are active parameters whose values were changed as a result of the optimization. And so notice down here, these are those two key reactions that we talked about, H plus HO2 going to O2 plus H2, and H plus HO2 going to OH plus OH. And you can click on reaction number for information, for example, reaction 35 here, which is H plus O2 plus water as the third body, forming HO2 plus water. So this is a reaction in which experimentally there's a good degree of uncertainty because of this high efficiency of water as a third body. And thermodynamic data for reaction 35. So this is what you get from clicking on it. And then optimization against a range of targets. So these are shock tube ignition delays and species profiles for laminar flame speed, prompt NO, HCN oxidation, reburning. And so these are a couple of examples. So these are the targets that I was talking about. And this is ignition delays from Siri and Bowman in 1970 as a function of temperature. And so these are the experimental data. And these are the tunings of GRIMEC going from GRIMEC 1.2 to GRIMEC 3.0. And this is a concentration profile for OH as a function of time from these experiments from 1995. And the tuning of GRIMEC to reproduce this. So this is the tuning of the whole of of these selected reactions within GRIMEC to reproduce this range of targets, and the parameters are optimized against this range of targets. So they're not just taking a single target and optimizing against it. They're taking the whole range of targets. So these are targets and optimizing against those. So these are some more examples, flame speeds, CH mole fractions. Again, this is a flow tube experiment by Peter Glaborg on ethane and NO. And here are the concentrations of the various species, CO, CO2, NO, HCN. And these are the predictions of GRIMEC. And you can see that they're not hitting the results exactly because what they're doing is they're tuning the mechanism across this whole range of targets to get what they see as the optimized mechanism over that range of conditions. Okay, so that's GRIMEC, and it is undoubtedly, it has undoubtedly been one of the most useful chemical mechanisms for the oxidation of these small hydrocarbon species that's been generated. And it's been generated in a rational way, taking the rate data that are available at the particular time the mechanism is constructed, and then tuning the parameters within the range of uncertainty. We'll come back to some comments on an alternative approach. One of the things that tends to happen is that some of the rate parameters just move out to the edges of their uncertainty. That's one thing. The other thing is that it has to be used as it stands. It has to be used as it stands and within the range of conditions under which it was optimized. You can't go to GRIMEC and say, oh, there's a better rate coefficient now for this particular reaction. Let's put it in. That would be a misuse of GRIMEC because of the tuning aspect of the way that it's been done. So the tuning is both an advantage and a deficiency of the approach because it's fixed in stone until it's re-optimized at some future date. So what you could do is, or what one could do, or the community could do, is to go back to GRIMEC, say, okay, we've got this whole host of new experimental measurements of some of these rate coefficients, reduce uncertainties in them, let's put them in, and then let's re-optimize. But that's the only way in which you could put the new rate data in. You'd have to re-optimize, and it's a big job. The other thing about GRIMEC is that you shouldn't use it outside its range of optimization. So the range of optimization was given there. So these are the conditions under which it's been optimized. And one shouldn't use it outside those conditions because it doesn't necessarily apply outside those conditions. Michael Franklak, many of you know, and Michael is one of the key instigators of GRIMEC. And this is a quote from a paper of his in the Combustion Symposium in 2007, which was the Heidelberg Combustion Symposium. He talked about a process, something which he calls process informatics, which is the use of e-science to help us as combustion scientists. And what he says is that process informatics relies on three major components: proper organization of scientific data, availability of scientific tools for analysis and processing of these data, and engagement of the entire scientific community in the data collection and analysis. And so this, in a way, is going back to the proposal that was made earlier on, that can we have a good set of mechanisms which are our best view of what's going on. Michael made an attempt to do this and set up this prime database, which still exists, and many people still contribute to it, but we haven't yet reached the situation where the whole community is working with this database and putting all of their data into this database, or allowing access to all of their data through the database, and the generation of good mechanisms by the community as a whole. So we're still some way away from doing this. So here's the prime group directory. So these are the different areas of combustion science that are referred to in it. So C0 to C2 refers to the elementary kinetics involved in these, with these species, C0 to C2. And these are the number of subscribers in principle. I'm a subscriber to this particular area, but really it's fallen into disuse and isn't really an active group. Some others are active groups. And so it goes on. These are all the different areas. TST down here, transition state theory. And so this is an example of a prime recommendation for this particular reaction, OH plus formaldehyde. And this is very much a sort of evaluation. So here's experimental data on which the analysis is based. The red line is the recommendation, and there's the prime recommendation there, the upper and the lower bounds. And this shows you the value that was used within GRIMEC. So this is the expression that's used in GRIMEC. Notice that over the region over which GRIMEC operates, which is up here, then the recommendation is very close to this overall recommendation here for OH plus formaldehyde. It's only when we get down to these lower temperatures that apply, for example, in atmospheric chemistry, that there are significant differences between the two. And so this at the bottom says is the comment on what was done. The best fit uses the Stanford shock tube data up here, as well as some of the room temperature experiments and some transition state theory results by M.C. Lin. Systematic provision of targets. One of the key issues here is that we need, because of these uncertainties that we talked about within these mechanisms, we need to be able to provide tests. And GRIMEC has used a wide range of tests, but they've been picked fairly randomly, just using what's available. What would be good would be if we had a systematic set of very well-tested experiments, which gave us a set of targets against which mechanisms could be tested and further developed. And so this is the Stanford group using shock tube data and excellent monitoring techniques to define the system. So this example here is heptane, and monitoring using infrared gas laser absorption to look at heptane and ethylene, OH monitored using UV laser absorption, CO and CO2 monitored using IR diode laser absorption at 2.7, 2.5. So taking these shock tube data, doing shock tube experiments, and defining the system as well as one possibly can. And then this is an example of a test of a mechanism against these shock tube data. So here's the time in microseconds down here. So this is for heptane. And here's the ethylene, water, OH, CO2. And here are the results that come from the mechanism, which allow you to understand how well the mechanism is doing. In this particular case, and this is the way in which we'll discuss this later on, what one really ought to be doing is including both the uncertainties in the experimental measurements and the uncertainties in the mechanism that come from the range of parameters. But this is undoubtedly a major step forward. And Hai Wang, who gave these kinetics lectures last year, has used the target data in his papers with Sheen. And so these are some quotes from the abstract. The precise nature of the measurements of Davidson et al. Impose critical constraints on chemical kinetic models of hydrocarbon combustion. So they're good measurements, and they provide critical constraints. Then we need to understand, this is a fairly complicated sentence here. What he's saying is, while an as-compiled prior reaction model can be accurate in its prediction of the detailed species, the kinetic parameter uncertainty in the model remains too large to obtain a precise prediction of the data. Now, what does he mean by that? What he's saying is that if we take a mechanism and put it into the model, then the rate parameters can actually give us quite an accurate description of what's going on, but the uncertainties in the rate parameters are associated with a very high degree, a very high lack of precision. So there's a substantial uncertainty. We're getting fairly close to the results, but the precision of that simulation is low. And then he says that constraining the prior model against the species time histories with the measurement uncertainties led to notable improvements in the precision of the model predictions against the species data, as well as the global combustion properties considered. Accurate data of global combustion properties are still necessary to predict fuel combustion. Well, let's go on to the next slide, and then let's come back and see what all this means. Okay, so this is what he's saying. So here's OH, and the experimental data is the solid line. The computed data are the dashed lines, what he calls the nominal prediction, and the dots show the uncertainty scatter. And what he's done to generate those dots is he's done simulations where he's allowed the rate coefficients in the mechanism to float across their uncertainty levels. And those are primarily uncertainty levels that come from, for example, evaluations. And then, oops. And then what he showed, so this is for OH and for ethylene. And the right panel is what he calls a posterior model, where what he's done is he's tuned some of these sensitive rate coefficients, or he's been able to reduce the uncertainty in these rate coefficients by comparing with these accurate shock tube data. And this is very much like what we talked about later on, and which we'll talk about, what we talked about yesterday, and we'll talk about in a few minutes, about this approach of Thomas Tarani of using direct measurements of rate coefficients coupled with indirect measurements, for example, ignition delays. And so Haiwang is doing a similar sort of thing here, in which he's taking the direct measurements, which have got significant uncertainties associated with them, and then combining those with these highly precise shock tube measurements of whole systems. And by doing that, he's able to get a model which can give not only accurate predictions, but also quite precise predictions with relatively small uncertainties. And so this is a really important conclusion, which is complementary to the approach that we talked about with Thomas Tarani, but coming from a slightly different approach.
Excuse me?
Yeah?
Does those data include the uncertainty of the thermodynamic data?
Of the thermodynamic data, I wouldn't like to say. I would be guessing. I would have thought, knowing Haiwang, it does, but you'd have to check the paper. Okay. Yeah, let's quickly go through this. So this is what we talked about yesterday. So this is a repeat of the stuff by Tarani, in which he says that the domain of feasibility of Arrhenius parameters is determined from all of the available direct measurements, and the optimal Arrhenius parameters are sought within this domain to reproduce the selected direct and indirect measurements. Okay, so what we said yesterday was Tarani took the range of rate coefficients. So this is H plus O2. So here's the thick red line, which is the Balch recommendation. The dotted red line shows the range of uncertainty of the rate parameters that were measured for H plus HO2, the total range the total range of measurements. And these lines in here are all different experimental determinations over different pressure conditions. So what he's doing is he's taking that range of values and allowing, in his optimization process, he's allowing the rate coefficient to assume any values within this range. And then what he does is he takes measurements of things like ignition delays, ignition limits for hydrogen-oxygen systems. So he's got several direct measurements, 9 direct measurements with 745 data points, 10 direct measurements for, this is for H reaction 2, H plus O2 plus M, and then 11 ignition time measurements with 79 data points. These are all taken into account in a very careful statistical analysis. And then by taking all of those together, what he was able to do was to significantly reduce, as we said, the uncertainty in the overall rate parameters. So this is the initial range of uncertainties in the rate parameters, which he defines as this envelope here, which covers all of the good measurements that have been made. This is the uncertainty range proposed by Balch et al., just by sticking a finger in the air and guessing what a reasonable range of uncertainties is. And this is, down here, is the optimized set of uncertainties. And so once again, what Tarani is saying is the same as what Haiwang was saying, and that is that it's possible to very substantially improve the precision of a mechanism and therefore of models by not only including the direct measurements of the rate coefficients, but also including what indirect measurements can say of them, what whole macroscopic systems can say of them. Okay, what I suggest we do is we break for coffee there, and then we'll carry on and finish this, this talk and then go on and talk about NOx later on.